the first correction to the scattering. That is, to the lowest order, we have this diagram, which was contributing minus I lambda. Okay. Then to the next order, we added a diagram like this. So this was x1, x2, x3, x4, and an x, and it was just contributing minus I lambda. Here it was x1, x2, x3, x4, and an x, and a y. Right? So this involved an integration over the internal loop momentum, and then I pointed out that it is a logarithmic divergence, and we just regularized it by saying it is log lambda upon c square. Now I want to do this a little bit more, well, probably not rigorously, but differently, because I want to introduce one technique called dimensional regularization, which is very often used in all gauge theory sections. So the dimensional regularization has the advantage that it sort of maintains the symmetries of the system, and if you want to renormalize non-abelian gauge theories, etc., this is the most powerful tool. At the same time, it is a little sophisticated. It requires a little bit more conceptual background to understand the renormalization by this. The way we have done originally, the scaling just was put in by hand, so we know if you change the scale how the coupling constant runs. Here it will not be so obvious, but we will do it in a slightly different way, and I will try to convince you that the result is the same. So we want to know what is involved in this computation. So let us again start with our amplitude, let us say for this process. So to the lowest order we had a minus I lambda. Then to the next order we found that it is equal to minus I lambda the whole square divided by 2, which is the 2 factorial, and then there is this 4 factorial square which got cancelled out because of the permutations. Then I had an integral here. Okay, so the integral was of the form integral d4k, let us say, upon 2 pi to the power 4. There is a Green's function for k, and then there is a Green's function for p1 plus p2 minus k. I will write this as k minus p, where p is p1 plus p2. Okay, so p1 and p2 are the two ingoing momentum. Now we also know that this is just one part of the piece. There is going to be one more term which involves, instead of p1 plus p2, replaced by p1 minus p3, and another one with p1 minus p4. So there are two more terms, which I will just keep it here as dot dot dot. But let us concentrate on this. So first we want to do a little bit of cleaning up on this. What we will do is that this term is minus I lambda. So let me write this again as minus I lambda. Here, when you do this, you will pick up two I factors. So maybe I should just expand it out. That will be clearer. Okay, so there will be an I over k square minus m square plus I epsilon. Then you will have an I over k minus p the whole square minus m square plus I epsilon. Okay. So let us take care of the I factors first. So this I and this I is going to give me a minus 1, and that minus 1 is going to cancel with the I square minus 1. So this is what you get. Okay. So the conventional way of doing this is to write this as just like this quantity. You write this as a minus I times this quantity. Okay, and you put an extra I here. So I into I takes care of this factor. The whole idea is to look at this expression and say that your lambda, if you take my minus I out, originally we had a lambda, and effectively it is going to be replaced by lambda plus lambda square by 2 times I times this integral. correct? Just look at it once again. This is minus I lambda, then I put another minus I and then kept an I here, so that I can throw away all these minus I lambdas. So originally if I had an expression for lambda, that lambda, finally we want to know how it gets renormalized. So you essentially going to replace this lambda by lambda plus this quantity. And also we are going to work in the Euclidean sector. So the moment I go to the Euclidean sector, this d4k will pick up an I factor. So you will have d4k Euclidean upon 2 pi to the power 4 and another I factor that gives you a minus 1 times 1 over, now it is k Euclidean square plus m square and 1 over k Euclidean, okay, k minus p Euclidean, so to speak, whole square plus m square. Okay, it is this integral which we want to have. So hereafter, for the sake of simplicity, I won't put this ke on the thing. We will assume that we are working in the Euclidean sector. So the integral which we want to study and remove the divergences in a sensible way is this quantity. Let me call this f of p square, because of Lorentz invariance it can only depend on p square, which is what we have called s. So once we have the final answer, I can replace s by t and s by u and add the three terms together. So this f of p square is given by minus integral over d4k over 2 pi to the power 4. Okay, I will keep the other two constants. There is a lambda square by 2 which I am going to add only in the end, upon 1 by k square plus m square and then 1 by k minus p the whole square plus m square. This is the object I want to study, and I know that it has a logarithmic divergence, but I wanted to remove the divergent terms in some systematic fashion. Okay, this is the whole idea. Now there is a slight trickery which has gone in, which you should check it out. It's not very important because the answers don't depend on that. When you do this Euclidean rotation, what you are doing is that you have a real axis on k and you are rotating like this, which means that in the second quadrant, second upper quadrant, and in the fourth quadrant, on the left bottom quadrant, you should not have any poles for this rotation to work. That is guaranteed by in this. I mean, you can just check it out that because that is the whole idea of rotating, that I epsilon takes care of it. Here it is slightly trickier because there is a p and an m and things like that coming in, and you will find that there is a range of p square up to m square where the poles are outside this region and you can rotate. Okay, so you are sort of assuming that the poles are not blocking your Euclidean rotation, which is for a particular range of p, and then once you have the final expression, you can analytically continue it. Okay. So there is, just for those who may read it in some textbook, I am mentioning that there is that complication there, but let us ignore that for a moment and go ahead. So how will we do this? The way we will do this is we will write this as an n-dimensional integral. We will put an n here. In fact, we will put it as n by 2 4 pi square. Turns out to be useful later on. Okay. So if it is an n-dimensional integral, you can presumably think of values of n for which the integral is convergent. The integral is perfectly well defined near k is equal to 0. And if you go to large values of k, it is going to go as 1 upon k to the power 4. So if you are looking at, for example, n is equal to 2, okay, then the integral is convergent. So we won't bother too much about what value of n we are going to choose when you do dimensional regularization. So the assumption is that there will be a range of n for which things are fine, and then we will analytically continue, or we will take the limits of n going to 4 right at the end of the calculation, where some terms will blow out and that can be isolated. So that is a trick. So let us look at this quantity, and there are various tricks to evaluate this. So the way we will do this is to write these two quantities as integral 0 to infinity e to the minus some parameter times that quantity. And this is something which we have done several times, so I am just going to do that. So you have minus integral 0 to infinity, we call it some variable t, not to be confused with the variable in that STU. So e to the minus, okay, let me write all the integration variables first. Integral over 0 to infinity t, integral 0 to infinity ds. Then I have this integral dnk upon 4 pi square to the power n by 2. Then we want to write these two differently as e to the minus, let us say s into k square plus m square minus t into k minus p the whole square plus m square. Okay, so let us make sure you understand that. E to the minus s k square plus m square integrated over s will give me 1 over k square plus m square. Similarly, this integrated over t will give you the other factor, which are the two factors which we have. So the whole idea is that the n-dimensional Gaussian can be done over this. Okay, that is the trick. So this will give me, if you look at the exponent, that is going to give me integral over minus integral over 0 to infinity dt, integral 0 to infinity ds, let me write it as e to the minus s m square and t m square. So it is s plus t m square, that goes for the right because that is independent of k. Then I have to do a k integration over the remaining term. Okay, so let us see what it is. What we have got left here in k integration is in the exponent we have a minus s k square that comes from this. Just make sure I don't make an algebraic proof, so follow it with me. Then I have a minus t k square plus p square minus 2kpt. Okay, these are all 4-dimensional dot products and all that, but they will all take care.
T will not be there.
Okay, T is outside, yeah. Okay, 2kpt. So this is equal to minus s plus t k square. Then I seem to get 2kpt. Then I have a minus tp square. Okay, so let us keep the minus tp square here. No, actually that will combine with something, so it is better to keep it together. Okay, minus tp square. So let me just write it out. Minus tp square. Okay, it is easier to do this. So this is just an expansion of that. So we want to complete the square. So you write it as minus s plus t into k minus 2pt upon s plus t the whole square. So let us check this. So this, if I square, I will get a k square, that will give me this term. Then when I do this, there is no 2. I will get 2kpt upon s plus t the whole square with a minus sign. That will become plus here, and s plus t the whole square will get cancelled by s plus t. So no, that is correct, because that is exactly what we want with the correct sign and order. So I only have to subtract out of it the square of this. So that will be, if I subtract the square of that, I will get, I'm going to subtract the square inside and with a plus here. So it will be plus p square t square upon s plus t the whole square. That is, the square of that will come, has to be subtracted. So I will have a minus sign here and a minus sign here, that makes it plus. And the square of that will be p square t square upon s plus t the whole square. This is okay. So this quantity, then I have a minus t p square here. So this can be written as, take the minus t p square outside. Will be this. Okay. So this nicely subtracts out. So one t will go away and you will have an s with a minus sign. Okay, this is what we have. So this is going to be plugged in here and we are going to do an integration. So the integration is shifted to from k to this. So that is our usual Gaussian. So it is going to be square root of pi divided by whatever is this quantity, which is s plus t, whole to the power n by 2. Okay. Then I have a 1 upon 4 pi square to the n by 2. That is the whole idea of keeping it as 4 pi square. So you take that 4 pi square inside. So you get 1, 4 pi, and this pi goes there. Okay? That comes from that integration, and this is left. So I have this into e to the minus st upon s plus t p square. Okay? This is assuming the algebra is correct, this is what we get. So let us see what happens next. So this is going to be minus 1 over 4 pi to the power n by 2. This goes for a ride for a long time. Then you have to do an integration over 0 to infinity dt, 0 to infinity ds, e to the minus m square s plus t minus p square st upon s plus t. This is what you get. Okay, let me make sure this expression is correct before going further. It is 4 pi to the n by 2, then s plus t to the n by 2, s plus t, both are minus with this one. Correct. Okay, so this is what we have. Now obviously this is a dt ds integration along the positive axis. If you think of t and s as two positive axes, this is a two-dimensional integration along the positive quadrant of t and s with s plus t and s plus t here, right? So is there an issue?
S plus t is s to n by 2 in denominator.
Oh yes, of course. There is an s plus t. I forgot. That is going to be crucial. S plus t is correct. Okay, so this is the expression. Now the obvious substitution is s plus t is equal to something and st is equal to something. So you have a change of variable. Now if you do that, you have to find a Jacobian. Okay, so I just want to teach you a trick. So normally that is the way to do this, and you have to find the Jacobian, transform to that and do this. But there is a trick to take care of it if you don't like calculating Jacobians. Okay, the trick is the following. You put an integral 0 to infinity, a Dirac-Delta function. Let us say d mu, a Dirac-Delta function of, let us say we want s plus t to be one variable. Put s plus t minus 2. This is nothing because this is 1. Okay, so you can put that in. And this is mu. None of this depends on mu, so you can carry the mu integration all the way through. So you do that first. So what you will get is that your f of p square will be equal to minus 1 upon 4 pi to the n by 2. Let me take my mu integration out. Integral 0 to infinity d mu. Incidentally, it is 0 to infinity because we know s and t are positive. So s plus t is positive, and I only need the positive range for doing the integral. So mu is taken out. Then I have an integral over 0 to infinity dt, integral over 0 to infinity ds, and 1 upon s plus t to the power n by 2 e to the minus m square into s plus t minus p square into st upon s plus t times a Dirac delta function on s plus t minus mu. We will play one more trick here. We will change one more variable because it is nice to get them all in a dimensionless form. So what we will do is that we will think of s as, we will change from s and t to two variables alpha and beta. We will put s is equal to, let us say, alpha mu and t is equal to beta. Okay, for a given value of mu, we are changing s and t integrations first. Mu just is, and we are just going to do the s and t integration. So we will do this. So that will get us minus, again 1 upon 4 pi to the power n by 2, integral over mu. Then here I will have an integral over 0 to infinity of d alpha. Okay, t is beta, so d beta, integral 0 to infinity d alpha. So I get two factors of mu there, so there's a mu square. dt is mu times d alpha, similarly, so I get two factors of mu. Then I get an 1 over s plus t. S plus t is going to be 1 mu, mu to the power n by 2. Okay, right, okay, all right. Mu to the power n by 2. Then s plus t, this is unnecessary, but we will do it this way. Alpha plus beta is going to be unity. So alpha plus beta to the power n by 2. Okay, so I had just written s plus t as alpha plus beta times mu and write this thing. So e to the minus m square. Here again I have a mu alpha plus beta minus p square. St is going to pick up a mu square on top, mu square into alpha beta divided by 1 mu, so that leaves a mu on top, alpha plus beta, okay, multiplied by Dirac delta function on mu into alpha plus beta minus 1. So everything is positive, so Dirac delta function of mu times this is just 1 by mu times that quantity, so that takes this mu out. Okay, this is what we have got. So now it is trivial to do the integration over alpha and beta. So let us do the integration over beta, keeping the alpha. But you have to be a little bit careful. Once I have done the beta integration, if alpha and beta exceeds unity, the Dirac delta function kills it. So once I have done the beta integration, alpha integration is limited to 0 to 1. Okay. So what you will have is minus 1 upon 4 pi to the power n by 2. Integral, now I will write the alpha integration first. This is this. Beta I am going to do, and then there is a mu integration, d mu. So here I have 1 over mu to the power n by 2 minus 1. Alpha plus beta is unity, so that doesn't come in. Then I have exponential minus m square mu, alpha plus beta is unity, minus p square mu, alpha into beta is going to be 1 minus alpha. Right? Alpha plus beta is unity. So this is what you get. Okay? So let me once again check that. Okay, I'll do this integral as well and then check. Okay, so this can be simplified. So there is a mu which I can take outside. times mu. Now let us call this quantity something. Let us call this x. Okay. So this is gamma function essentially. So we just want to get the factors right. So you have an x here, and this is x mu. So x mu I'm going to call some rho or whatever. So I want an x mu here. So you put an x in this. Then on top you put x to the power n by 2 minus 1. So nothing has changed. Then you put another x here. So you had to divide by that x. That makes it 2. So you get this to be equal to minus 1 upon 4 pi to the power n by 2 integral 0 to 1 d alpha of a gamma function. So what is it a gamma function of? It is gamma of n minus t to the n minus 1 e to the minus t will give you gamma of n. So it seems to give me here gamma of n by 2 minus 1. That is wrong. It should be n by 2 minus 2. So there is one factor of mu missing somewhere. So let us see where that was missed out. So I had two factors of mu here. So let me just check that out. There is one factor of mu which is missing somewhere. There is a mu to the n by 2 is correct. Then you pick up two factors of mu here, and one factor of mu goes away. So it is mu to the power on top 1 minus n by 2. I go from the denominator versus numerator. Yeah, okay, fine. So up to this is fine before we put this x in. Let us just redo this part. So this was what we had. So it is mu to the power 1 minus n by 2. This is what we have. Let me just make sure of that. U to the power 1 minus n by 2, u to the minus this. Yeah, this is fine. This is t minus n minus 1. That means this has to be 2. Okay. So what you will get is that, let us redo this. Now you will put an x here. So I had to put in the denominator x to the power 1 minus n by 2. That cancels it out. Then I had to put here another x. Then I have to put another x in the denominator. That makes it 2. This is how it should go. Okay. Then the mu x is the integration variable everywhere. Therefore, this will be equal to minus 1 upon 4 pi to the power n by 2 integral 0 to 1 d alpha. This is going to be 1 over x to the power 2 minus n by 2 times this integral is going to give me a gamma function of 2 minus n by 2. Okay. Now this quantity can be written on top as n by 2 minus 2 n by 2 minus 2 of this m square plus p square alpha into 1 minus alpha into n by 2 minus 2. This is what we have. So gamma of course comes outside the integral. Gamma of 2 minus n by 2 integral 0 to 1 d alpha of this integral. Okay, this is what we are finally going to end up with. This is fine. Gamma of n by quantity m square into alpha, this n by 2 minus 2. Everything is fine. At this stage, we notice that this has some weird dimension, m square to the power n by 2, and we have to take limits on n. So we don't want dimensions to go wrong anywhere. So as a result of which, we will just divide this by a scale mu square. Okay, everything is being called mu, but the other mu's have disappeared, so it's alright. So this is some mass scale. Mu has dimensions of mass, all these has dimensions of mass, so I have divided it by this, so I have to multiply it by that. So it is mu to the power n minus 4. So mu square times this quantity will be equal to n minus 4. Okay, nothing has changed because the mu just cancels out in both the things. Finally, you will find that this mu is going to be our renormalization scale, etc. At this stage, we have to take the limit of n going to 4. So we have done the integral. You can do this integral, but it is better to leave it like that. So if you take n going to 4 limit, this becomes gamma of 0, which we know is divergent. So we want to do this thing a bit carefully. Okay. Now the way I would have done this is that to define either n by 2 minus 2 as epsilon or the other one as epsilon, what I defined 2 minus n by 2 as epsilon. Okay. So let us think of 2 minus n by 2 as a small quantity epsilon. And we are interested in epsilon going to 0 limit, especially in this quantity. Okay. So let us work that out and see what divergent terms come in there. Okay. First of all, when n goes to 4, this just disappears, which means that the divergent term should have some mass dependence. That is, this divergent term, which is finally going to pick up, has some kind of an implicit mu dependence, which will come back and hit us later on, but for the moment we will forget about it. There is no problem here. That also can be written down. So you will find that your f of p square has the form minus 1 over 4 pi the whole square. That part is fine. Then we want to look at this gamma function.
Excuse me, sir.
Yeah.
Sir, about that divergent term having mass dependence, can you please repeat?
Okay, what I meant was that I am now going to put n is equal to 4 here, which means that I will keep a mu square dependence on that integral, which when I expand it out, it will have all kinds of mu dependence coming in. Right? Because right now I don't want to expand it, because if I put n is equal to 4, this quantity will just go away. But that is not what we want. We want to do a more careful Taylor series expansion in order to pick out the divergent term, which is what we are going to do. So when you do that, in the end you will find that that has a mu dependence. But there was no mu in the problem. I put it in by hand at this stage. At this stage the integral is independent of mu. Now only because I am taking away this mu dependence by taking n is equal to 4 and keeping the mu dependence there on the divergent term, the divergent terms has an implicit mu dependence. You can think of it as some log lambda upon mu, like in our previous things. Okay, but it will be clearer when we do it in a moment. Okay, so just watch out for that. I am just saying that mu has disappeared, which is a little peculiar, so you should notice that. Now let us look at this gamma function. So you have gamma of 2 minus n by 2, which we will write, let us see, we will write it as gamma of 3 minus n by 2 upon 2 minus n by 2. This is just using the fact that gamma of 3 minus n by 2 is argument minus 1, which is 2 minus n by 2 times gamma of 2 minus n by 2, and that 2 minus n by 2 I have explicitly cancelled it out. Okay. So now we want to look at this quantity in terms of your epsilon. 2 minus n by 2 is what we have called epsilon. So 3 minus n by 2 is 1 plus epsilon. So I have an 1 plus epsilon here, and this is epsilon. We want to know how this behaves when epsilon goes to 0. Okay. So you do a Taylor series expansion on top. Gamma function is just a function. So it is gamma of 1 plus gamma prime at 1 times epsilon divided by epsilon. Okay. Now gamma of 1 is 1, so that is not an issue. Then of course next terms etc. are epsilon square and all that. Gamma prime at 1 happens to be a quantity called minus gamma, which is an Euler's constant. You don't really need to know what it is. It is just that it is some finite quantity which you can look up. Okay, so this is the Euler's constant times epsilon. So this is what you have. So the front gamma term is now going to have an epsilon dependence. It goes as 1 over epsilon minus gamma. So you see that there is a divergent piece emerging from it. Okay, fine. Now let us look at the rest of it. There is an integral 0 to 1 d alpha, some quantity to the power minus epsilon. Right? So this is some bracketed expression which is this to the power minus epsilon in our notation. This we will write as, this bracketed expression we will write as exponential of log of that expression. Therefore this is exponential minus epsilon log of whatever is inside the bracket. And we are interested in the limit of epsilon going to 0. So now you can do a Taylor series expansion. So this is 1 minus epsilon log that bracket expression. We only need up to leading order. Okay. So that integral is going to give you 1 minus epsilon log m square plus p square alpha into 1 minus alpha upon mu square that's it, to this order which we are interested in. Okay. Now let us again separate the divergent and convergent term. So I have minus 1 over 4 pi square, 4 pi square. So let us multiply this out. So this integral gives me first 1. Integral d alpha 1 is just 1. So then the remaining integral sits there. So this is going to be minus integral 0 to 1 d alpha of these quantities with an epsilon in front. So if I expand it out, I get a 1 over epsilon from the first term. Then I get a minus gamma multiplying these two together. Then I get epsilon and this. So that will be minus integral 0 to 1 d alpha log m square plus p square alpha into 1 minus alpha divided by mu square. Okay, what else is remaining? This we have multiplied by 1, this we have multiplied by 1, then this we have multiplied by this, then we have to multiply this by epsilon. That doesn't contribute when epsilon goes to 0. Okay. So we have nicely separated out the divergent and convergent terms. The divergence is all absorbed in this 1 over epsilon factor. When epsilon goes to 0, everything else remains fine. Okay, that you can verify. I mean, I'm not going to do that integral. Actually, that integral can be done, and there are something interesting in it, but we don't need it. So there is some finite path, and then you have this 1 over epsilon. So this whole answer can be written as minus 1 upon 4 pi the whole square 1 by epsilon plus 1 upon 4 pi the whole square into gamma plus integral 0 to 1 d alpha of this whole quantity. Conventionally, this is written as 1 minus log mu on top. Alpha into 1 minus alpha. Looks right to me, but let me just check. And this is the final answer. So there is going to be 1 upon 4 pi square gamma minus d alpha integral log. Okay, seems to have got an extra 4 pi in it. Not that it matters. Oh, that is fine. That is because instead of using mu square as the parameter, I have used 4 pi mu square. That doesn't matter. So this is what we get. Okay, this is the answer. So when you look at the handout, you may find an extra 4 pi factor, which is irrelevant. So what does it mean? Now that we have isolated the divergence by this procedure, what can we say about it? Remember that what we have been working with is this also. Correct? So this is the quantity which we have laboriously evaluated. Now we can plug it in and ask what happens to the scattering amplitude, which is what we wanted to compute. So when you do that, what you get is this. So let us see. The expression which we want to calculate, which is going to replace your lambda, will be lambda plus lambda square by 2 and minus 1 times that is what we have evaluated, and you find that that term is minus 1 upon 16 pi square 1 over epsilon, which is here, plus a finite part. Okay, so here is a finite part which involves this log mu square, etc. I need the finite parts mu dependent, so I'll just write it like this. There is a, okay, maybe I should isolate the mu dependence right away, plus a finite part, but just for the sake of argument, let me isolate the mu dependence, which is 16 pi square. Okay, and log mu square will give me 2 log mu. This is just a constant. See, you can take this log mu square and minus log of this and do the integral over alpha on both. So this is independent of your mu. The mu dependence which we want is coming from this. So that is just going to be some minus log mu square. Okay. So this is going to be this into a minus log mu square plus some, which I don't care because it is a finite part. I mean, I do care because in the end that is what is going to give me the scattering amplitude, but right now I am going to concentrate on the renormalization part of it. So this is what you get. So the idea now is to play the same kind of a game. This is part of the finite part, so I am not going to worry about it. But I will pick up this whole thing and I will call it some lambda physical. So I will say that your lambda physical is going to be lambda minus or plus lambda square by 2 minus 1 over 16 pi square 1 by epsilon. Okay. Therefore, I can now go back and write everything in terms of this lambda physical, which is the same old game. You write lambda as equal to this quantity, to the lowest order it will be just lambda physical times this quantity. Okay. So when you look at, once you have done that, this entire thing has been replaced by this lambda physical. So this expression is going to become something like lambda physical, which is the product of all these quantities. Then you have got a lambda square by 2 times some quantity, but that lambda square by 2 I can now replace by lambda physical square by 2 times this whatever is the finite quantity which we have evaluated. So as I said, this you don't have to really worry about this. The whole thing is equal to that integral over d alpha of log mu square upon this quantity. Okay, so that is what I have put as this bracketed expression. So we have got the relevant amplitude entirely in terms of lambda physical, which is defined by this. Now, how do you get the running of the coupling constant? Here the way you do this is slightly different, but let me just make sure the sign conventions I have used is all correct. I mean that I have not, this is lambda physical minus 1 upon 16 pi square, yeah, that is correct. And the final expression is this plus lambda physical square by 2 times that f phi, yes. Now what we will argue is that this lambda physical should have a mu dependence, which should precisely cancel the explicit mu dependence in this. Okay. So what does that mean? What it means is that when you do a computation and find this amplitude, that amplitude should not depend on mu. So the derivative of the right hand side with respect to mu should vanish. So let us see what that is. Suppose I just call this for a moment as some f, the quantity inside it. Okay. Remember that there is one more complication. All this was done for one diagram, which is with a p. Actually, you have to write there f of s plus f of p plus f of u. Okay, so there are three of them. So there will be 3 log mu square coming up. This log mu square which I have found is common to all of them. There will be one term with p square, one term with p1 minus p3 the whole square, then a p1 minus p4 the whole square. But all of them will have a log mu square. Okay, so there will be 3 times that log mu square eventually coming. Okay, so let us see how that thing works. So what we are going to do is to say that 0 equals derivative of that with respect to mu. So d lambda physical by d mu, that is the first term, plus you have one term which is not going to be relevant, but I will write it down anyway. Lambda physical times d lambda physical by d mu times that quantity there, which we have called f. Then you have plus lambda physical square by 2 df by d mu. So df by d mu is coming from this. That is going to be minus 3 over 16 pi square. 3 because there are 3 factors of log mu square as I told you. Derivative of log mu square with respect to mu, that is 2 over mu. This is what you will get. Now if you work this out, you are going to find that it is already multiplied by a lambda physical. So this is one higher order term compared to what we are returning. So therefore this is not going to contribute. That is, you will find lambda physical by d mu already scales as lambda physical square. So this quantity is scaling as lambda physical square, and then you are multiplying it by another lambda physical, so it is lambda physical cube, which we are ignoring. So this equation tells you that d lambda physical divided by d mu equals, because it is 0, move it to the side, 3 over 16 pi square lambda physical square and that mu I would like to put it here. This is, once again we have derived the same result which we had. When we did everything non-perturbatively, we got exactly this. The way the coupling constant, physical coupling constant varies with log mu, because the mu, d mu gives you d with respect to log mu, was some 3 by 16 pi square times lambda physical square. Okay. Then we did this by a slightly crude way, by just keeping the logarithmic scaling and then calculated the quantity. And here we have done it a little bit more formally using the dimensional regularization. So all the results tell you that this is what is happening. So let me try to summarize the physics behind it. So we again use the same argument that we have calculated this amplitude, divide them up into a finite part and a divergent part. Then we incorporate the divergent part into a physical coupling constant. in somewhat old-fashioned renormalization theory, you will stop there. You will say that you have expressed everything in terms of physical quantities and you have got a thing inside which depends on some finite quantities, but it has a renormalization scale mu square. Usually that mu would be set to some physical scale in the problem. In this particular case, you could have put mu is equal to m, for example. That is one choice. Then you will claim that the lambda physical which you measure from the experiment is evaluated at that threshold scale, and then any other value can be found by just substituting it. A slightly more modern approach or a better approach would be to say that the lambda physical which is here actually contains information about mu, because this is in response to Pawan's question that originally when we did this calculation, we put in a mu and took out a mu. Then when n goes to 4, that mu went away, but the mu dependence on this hung around. So the other mu is actually hiding inside this epsilon, okay, because that is the term which we threw away. So in some sense, when you do the renormalization, the renormalized coupling constant should have information about mu, and how exactly that information is encoded is given by this equation, saying that nothing should finally depend on mu. So this lambda renormalization should run in such a way, renormalized or physical coupling constant has to run in such a way that the final answer is independent of where you are evaluating. So you could have actually chosen any lambda physical and any mu, done the experiment, figured it out for what mu is what lambda physical, and then you could have used any other scale exactly the way we did. Okay. So this is one way of thinking about the whole. So that is all which I wanted to say as far as this is concerned. But I will conclude with just, because we don't have time to do mass renormalization in any great detail, but I just wanted to show you roughly, very roughly, where it comes from. Because we have done the coupling constant here, and in the non-perturbative approach we had renormalization of both mass and the coupling constant. So let me just try to give you one class of diagrams in which it comes from. So these are the diagrams of the following kind, called tadpole diagrams. Remember that, because that is the phrase which people will use. So then you take the propagator and add to it 2 tadpoles plus 3, etc. So of course there is a free diagram here. So this is your full propagator when you take a whole lot of them into account. So what does this correspond in mathematics? So you start with some propagator. So we want to know what is the full propagator, summing up this geometric series. So you start with the original propagator G0 in momentum space. So that is just I over p square minus m square plus I epsilon. Then you add to it the next one. Next one will be, you have a G0 that will take care of going from here to here. Then something is happening here. That amplitude, let me just call, by convention it is put as minus I times something. So I will call it minus I times B. Then you have another G0. G0, this is that amplitude, another G0. Then the next one is similarly with one more set. So that will be G0 minus I B, G0 minus I B, G0 plus 6. This is equal to that diagram. Okay? Now there are different ways of summing it. It's just geometric progression. So one way of doing this is to say that, okay, let us see, G0, what would I like to do here? I can take this much out plus G0 minus I B. If I take that out from the rest, I will have again G0 plus G0 into minus IB G0 plus S. Right? It's the old way of summing up the geometric series. So this quantity is nothing but G itself. So you replace this whole thing by G again. and then you solve for G. Okay, so this tells you that this is right hand side is equal to G naught into 1 minus I B G. So 1 upon G naught, or rather 1 upon G is equal to 1 upon G naught into 1 over 1 minus I B G. Take this quantity to this side. So that gives you 1 upon G minus IB is equal to 1 upon G naught. Make sure you understand this. I have taken the reciprocal. This is 1 upon G naught and 1 upon 1 minus IBG. Then I am going to take this 1 upon IBG here. So that when I divide out, I get 1 by G, and then this G cancels and I get a minus IB. That is equal to, on the right hand side, 1 upon G. So that tells you that 1 upon G is equal to 1 upon G naught. There is no mass renormalization inside so far, but it will come, plus I times P. Right? So this is what I want to find, this is what I know. Okay? What is this? 1 upon G naught is 1 by I P square minus M square plus I epsilon divided by I. So divided by I makes it minus I times this quantity. Then I have plus I times P. Therefore 1 by G is nothing but take an I out, or rather take a, take a minus I out. P square minus M square. So I have taken a minus I out, so that will be another minus B plus I epsilon. Make sure signs are right. Minus I P square minus I M square plus I epsilon is from the first term, and this minus gives you a plus IB, which is the second. Okay? So what does this mean? This just means that you are replacing M square by a renormalized mass square, which is just M square plus B. That is the answer. Okay? So the net effect of all these infinite number of these tadpole diagrams is to just shift your mass K from original M square to some B. Of course, the B is the amplitude for this process, which if you do an integral over d4p, it is d4p upon 1 upon p square minus m square plus I epsilon, which is divergent. You can play the same trick. You can go Euclidean and write 1 upon p square plus m square as integral 0 to infinity dt e to the minus t p square plus m square. Do the p integration, then you will have something, and you will find it is both quadratically and logarithmically divergent. And it will correspond to what we have done in the non-perturbative method, but it takes fair amount of work to show the equivalence, so I won't do that. So this is what you get. Now, as I said, this is a little crude and not a complete honest calculation, because if you have lambda order here and then you take lambda square order, you have to take into account all kinds of diagrams of lambda square order. For example, to lambda square order there are diagrams like this with two vertices and they are connecting together, right? So you could have added terms of this kind. Right? And they produce another kind of divergence. It turns out that it shifts the mass and it also changes the residue at the pole. See, in this way of doing things, 1 upon G was this. So G is equal to I over this quantity. So the pole of the denominator, that is 0 of the denominator, where the pole sits, is p square equals some m renormalized mass square. But the residue at the pole was still unity. When you do these things into account, you will find that that residue also changes, and that involves something called a wave function renormalization. Okay, so that is essentially the part on mass renormalization which I wanted to tell you. You should know that if you have tadpole diagrams and you sum it up, you do get this. I mean, that is the scope of this course. I don't think I want you to do more detailed things. There is just one more comment which I wanted to mention, which again we don't have time to do. When you have two particles with momentum P1 and P2 scattering off. Okay, so let us take this this loop which we calculated to, let us say, P3 and P4. Okay, and you have a finite expression, and when you do the integral, you will find that this integral has peculiar branch cut kind of a thing in the logarithm. When the quantity s, which is P1 plus P2 the whole square, crosses 4m square. So there is an s minus 4m square will come in the logarithm. I will try to throw it in the handout. It is not needed for your exams or anything, but if you are interested, you can just read it out. That is something which is very physical, so you should know what is going on here. The point is, when you are scattering two particles with momentum, P1 plus P2 is the center of mass momentum, and when the center of mass momentum square is greater than 4m square, or whether the energies are greater than this 2m, it can produce particles. So you can end up two particles hitting each other, and you can end up producing 4 particles. Okay, so there is a threshold for fire production which gets crossed, and the amplitudes know about it. When you do the calculation, you will find that it shows that there is a threshold for fire production at that point, s minus 4m square. So the finite part of the amplitude which you have computed contains fairly valuable information, but I mean, we have run out of time, so we don't want to do it. Okay, I think that is all I had to say. Questions?
So two factor.
There is a two factor. You see?
No, how is that two factor?
That two factor in that lambda physical square. Yeah, because it was log mu square. We are differentiating with respect to mu. So log mu square I write as 2 log mu. So you get a 2, then derivative with respect to log mu gives me 1 by mu. Yeah, I think that 2 cancels with that overall 2. So I remember the result as 3 over 16 pi square. I think that is correct. Let me just check. Yeah, that is correct. 3 over 16 pi square, when you do the running with respect to log mu, is the correct coefficient. That is what you would have got even earlier. Yeah.
So question not related to this, but related to the Riemann zeta integral we have done there.
Right.
I found in book they said it is meromorphic continuation rather than complete analytical continuation.
That is true.
Is that there are finite discrete singularities? Those are playing role for making it negative fraction, or what means what?
How do you give a definition?
Mathematically good things can we get? Because it means like we're summing natural numbers and getting negative fractions, which is not mathematically consistent. Means
but that is what I have been trying to tell you. That is mathematically consistent.
Yeah, but where we get the consistency?
The consistency is that you need, you have to view mathematics in a slightly different way. I mean, there are people who will argue that negative numbers do not exist. And a lot of Pythagoreans thought that irrational numbers do not exist because you cannot construct them geometrically. Right? I mean, then until they found that root 2 can be constructed. So the mathematics progresses by saying what are your rules of logic. So there is a particular way of handling. See, there is an entire book by Hardy on divergence series. So the whole idea is that if you have series which are divergent by the normal procedure, how do you try to give meaning to it? I mean, one way is to say it has no meaning. It is just like saying that you can't subtract 5 from 3. Because when you think in terms of apples, if you have 5 apples and you eat 2 apples, you have 3 apples. But if you have 3 apples and you eat 5 apples, how many apples? You'll say it is meaningless because I can't eat 5 apples if I have only 3 apples. Okay? But then people say, no, let us not do that. It would be nicer and more enriching experience to have negative numbers, and you extend. So in the same way, normally we deal with convergent series, and you say that the divergent series are meaningless. But there is a very decent, respectable branch of mathematics where you deal with divergent series and you give its rules of manipulation, like how to multiply them together, how to add them together, how to subtract, and how to work out, etc. And one very powerful tool for doing this is either analytic continuation or meromorphic continuation. I mean, in physics we use it interchangeably.
Because, sir, what we are doing is we are saying the series like Euler's proof we see. They are not absolutely convergent series. So if series is not absolutely convergent and we are saying it converges by also some different method, then
Yes.
it is like for some series we can say that though they are not absolutely convergent, but they converge in some other sense.
No, in the sense of divergent series. Yeah.
Yeah, but I like to have reference which can.
Okay, so
which can say how
Hardy has a
meromorphic-
book on analysis,
Yes.
which is a very good reference for that. Now, actually, most of the questions which you are asking is at such an elementary level that you don't need to even go up to 30. All that you need to do is to read a good complex analysis book on analytic continuation gamma function. Don't look at zeta function, because zeta function is also related to a series, and that series you think is divergent, and therefore there is an extra confusion. Take normal gamma function and evaluate it for some minus 13.6. If you go to table, they will give you a value for gamma of minus 13.6. Except for negative integers, gamma function is well defined. There will be graphs of gamma functions and they will give you a numerical value for it. Now you go back to the definition of the gamma function integral. This integral 0 to infinity e to the minus t, t to the n minus 1, and you put for n minus 13.6, that integral is clearly divergent. Right? So this is the point. How can I say that this divergent integral has a value which is 40.6 or whatever? So you have to first understand that. If you understand that, you will understand the Riemann zeta function. The divergence in Riemann zeta function comes because we are adding numbers. Divergence in gamma function is lot more visible. It is an integral which near 0 is divergent. Nevertheless, people say it has a finite value. How do you do that? You do that by saying that first you prove a result that gamma of x into gamma of 1 minus x is equal to some pi over sin pi x. Now, sin pi x has poles that x is equal to some integer. So, if x is some integer comes in there, so that there is a negative integer, you have a problem, because we know gamma of n is well defined. So, gamma of 1 minus n for integral values of n, which gives you 1 minus n negative, should have poles. But if it is not an integer, then I know that the right hand side is well defined, left hand side both the factors are well defined. Knowing one factor, I can find the other factor. But if I look at it in the form of integrals, I find that it is divergent. So this is what you have to come to terms with. And once you do that, then zeta function is just one step. I mean, the fact that zeta function, see, you just think of zeta function being defined for negative integral values of the argument. Just like gamma function, you look at it for negative integral values. Then don't worry about the fact that zeta function is also given in terms of sum. Think of zeta function as an integral representation. And then ask how I analytically can. That is the right way to think about it. Hardy analysis is a good place because it has a lot of details on that. I'm quoting from memory, but if I find some other book, I will tell you. Yeah. There is a book called Divergent Series by itself. I mean, I don't remember who the author is. I'll see where to find it. Any other question?